stack. Uh, yeah, so how we do stacking and twisting of different van der Waals materials. So what I will do is I will start, this is a brief outline of my talk. So I will first introduce you to this field of 2D materials, and then I will talk about the concept of 2D alloying and how you can use this 2D alloying techniques to engineer structural phase transitions, and what are the other ways by which you can engineer structural phase transitions in 2D materials. And so this is basically some part of the work which I have done as a part of my postdoc. And this is what actually got me interested into this field of growth of 2D materials. And what are the possibilities or different kind of experiments that one can look for in these kind of materials. And then after that, I will talk about some of the work that I'm currently involved in. So we have been trying to make 2D materials which are having different stacking orders, and how we identify these, stacking configurations. And then after that, I will talk about how we make the twisted bilayer 2D materials and how we study the coupling between this mechanical and electronic degrees of freedom. Basically, once you twist the angle, the band structure changes, and how this can be studied or this can be characterized by using spectroscopy. And towards the end, I will also talk about some of the recent advances in the CVD growth of 2D materials and heterostructures, which we are currently looking for in our lab. So, as all of you are familiar, so 2D material field actually started with graphene, the exfoliation of graphene in 2004, but it has expanded enormously since then. And now, if you see, you can see that there are a lot of different, classes of these 2D materials based upon the interesting electronic behavior or electronic phases that one can see. Okay, so you can classify them as semi-metal semiconductors. Then you have topological insulators. Then you have metallic 2D materials. Then 2D materials which can be superconducting. Then insulating like HBN, which we use as dielectrics or as substrates. Then recently in this class, we also have the magnetic 2D materials, which are also very interesting in its own nature. And one of the important thing that actually two of the important things that I will be talking in this, to you today will be about the polymorphs of TMDs. So the interesting part about the transition metal dichalcogenides, this is the class of layered materials which actually have several different crystal structures. So you can have in, either the 2H phase or you have the 3R phase. These are basically the trigonal prismatic structures, but differences in the stacking. And you can also have 1T phase, which is having octahedral coordination, and the distorted 1T phase. Okay, so there are different polymorphs of TMDs, and as I will explain later, each of them has interesting, properties in their electronic band structure. And the other aspect that I would like to talk to you about is the twistronics. So twistronics is basically the name given to the field of electronics that is emerging from the variation of the twist angle of these van der Waals materials. So you can see that by rotation of this, one material over the other material, you can see that periodic patterns are arising, which are basically giving rise to superlattice structures. And these can have interesting effects on the band structure as well. So I will start the talk with transition metal dichalcogenides because this is one of the major area that I'm currently working with. So let us see what are the salient features or what are the interesting features in these materials. So the first thing is they can have a variety of electronic phases. So if you look at the periodic table, so this is a part of the periodic table from where most of the TMDC materials are, so this is the transition metals, and these are, coordinated with sulfur, selenium, or tellurium, and you get the transition metal dichalcogenides. And you can see that they have a large number of electronic phases. You can have metallic, insulating, charge density waves, superconducting, topological phases, and depending upon whether you are having 2H bands, 2H structure or 1T structure. Now, another interesting feature in some of the semiconducting TMDs is the indirect to direct bandgap transition in the monolayers. Okay, so why this happens? So here you see the monolayer. You can see that the conduction band and the valence band. So the edges of these are at the same K point. But as you go to bilayer or to bulk, you can see that now the conduction band here basically at the gamma point, this is basically arising because of the hybridization of the pz orbital of your chalcogen, and that is basically changing as you so as you go to the quantum confinement in the monolayer. So as you increase the number of layers, the hybridization of this pz orbital changes, and that gives rise to changes in the band structure. So finally, you go from a direct bandgap structure to an indirect bandgap structure. And another interesting aspect is the valley and spin dependent optical and electronic properties. So I will not go into the details of it, but what you can see is that because these transition metals are having heavy metal atoms, you have a large spin orbit coupling, and that gives rise to the spin orbit split valence band edges. And interesting aspect is if you're looking at, say, a monolayer of MOS2 or WS2, now there is no inversion symmetry. Okay, so because the inversion symmetry is broken, now this K and K plus points are basically which are here in the points in the Brillouin zone. Now these are basically non-degenerate. And because of that, you can see that now you can excite the K plus electrons in the K plus valley with the sigma plus polarized electron, the circularly polarized electron and circularly polarized light. And this is the sigma minus circularly polarized light. Okay, so this is also interesting because it gives us a different feature how to independently tune the population of the different valleys using light. And finally, this is one of the very important aspects, and which gives rise to a lot of interest in this field. That is, there is very strong light matter interaction in these materials, and these materials also have excitonic features which are evident even at room temperature. So the excitons in these materials, they are having very high binding energy, and because of that, you can observe these excitons even at room temperature, as compared to most of the other semiconductors where the excitons are visible only at very low temperature. Okay, so this is the interest in the transition metal dichalcogenides. Now, let me also give you a brief introduction to the topic of polymorphism in TMDs. So, by polymorphism, what I have already mentioned to you, so you can either have the coordination of the transition metal to these chalcogen atoms in a trigonal prismatic way, or they can have a octahedral coordination. Now, the difference between these are, so if you are having a trigonal prismatic configuration, you can see that because of the crystal field splitting, now there is the dz square orbital, which is now lower in energy, whereas in the octahedral configuration, the lowest energy is basically for the dxz, dyz, and dxy. Now, as you can see here, now here there are two electrons which are occupying the lowest energy configuration. And and here you are having two electrons which are here in these two orbitals, and also there is one unoccupied orbital as well. So because of these, now if you calculate the band structure, you see that for the trigonal prismatic geometry, you get a semiconducting behavior, whereas in the octahedral coordination or the 1T phase, you have a metallic band structure. Okay, so this is another interesting aspect that you can, if you can change the coordination of the transition metal ion, then you can go from a 2H to a 1T phase, which is also correlated with a semiconducting to a metallic phase. Okay. Now, so as I told you, so you have this 1T phase, then you have in the trigonal prismatic configuration, you have both 2H and 3R configurations. And in 2H, basically the stacking is ABA, BAB, whereas in 3R, you see that it is ABA, BCB. So this is basically how the stacking is different for the 2H and 3R. And this is also very interesting because if you see here in the 2H phase, you can see that the bilayer of this TMDs, they are having inversion symmetry. Whereas in the 3R phase, it is equivalent to like say two single layers of TMDs, which are now slightly shifted from slightly shifted in one direction. Now, because of that, you can see that there is a lot of difference in the band structure. So this is basically the band structure for the monolayer TMD, where you have a direct band gap. And then this is for the A prime stacking, where this is basically your 2H stacking here. And in this case, you can see that now you are having an indirect band gap, but the layer 1 and the layer 2, the points are, the energies are basically degenerate. Whereas in the AB stacking, now you can see that because again you have an indirect band gap here, but the main difference is that when you're talking about excitations, in the case of AB stack WS2, so you can see that there is a spin and valley locking, because it is just like how the single or how a monolayer of WSE2 or WS2 functions. So the optical selection rules which hold for the monolayer will hold true for the AB stack or the 3R stacked WS2. But whereas in the case of A prime stacking, now there is inversion symmetry is restored in the system. And in this case, now you can have basically excitations which are happening within each layers. So this gives rise to features like spin valley locking in the case of AB stack WS2 bilayer and spin layer locking in the case of A prime stack WS2 bilayer. So these are some of the interesting aspects of of the different type of polymorphs in the transition metal dichalcogenides. Now, what I'll do is now I will start describing some of the interesting aspects of the work that I have done previously, and then later on I will describe the work that I'm doing currently. I joined Rice University, and at that time there was a lot of onus on CVD growth of 2D materials using using different kind of precursors, and what all you can do, whether you can make heterostructures, whether you can make alloys of 2D materials. So one of the work that I was primarily involved is in the field of how to make 2D alloys. So we started with these materials. So we had WS2, MOS2, WSE2, MOSE2. So these were all the semiconducting TMDs. And the idea was, if you can make an alloy of all these four, then you should be able to tune the band gap from 1.6 EV of that of MOSE2 to 2 EV, which is that of WS2. Okay, so band gap engineering was an interesting aspect. And with this in mind, we had tried to grow these quaternary alloys, which are having molybdenum, tungsten, sulfur, selenium, everything. And so what we used to do was we keep the precursors for the tungsten and molybdenum, and then you place your silicon wafer, silicon dioxide wafer on top of that. And then the sulfur or selenium mixture is sulfur and selenium mixture is kept in the lower temperature zone, and and during when you have an argon hydrogen flow, you see that at the right temperature, as you vary the temperature between 650 and 800 degrees Celsius, you can see that there is a good 2D alloy formation of all the four elements here. Okay. So this was the beginning. But now this next question I asked was whether, so this is like everything is in the 2H phase, and we know that all these are basically stable in the 2H phase. So next what I tried to do was I tried to take two different parent materials. One is MoSe2, which is stable in the 2H phase, and another one is rhenium selenide, which is stable in the 1T prime phase, a distorted 1T phase. Okay. And the question is, if you alloy these two, whether we can have a phase transition from 2H to 1T prime. So our the DFT calculations which we had done actually showed that above 40% of alloying of rhenium in MoSe2, you can actually see that there is a phase transition. And the reason for this phase transition is, so when you add rhenium, now rhenium has one extra electron when compared to that of molybdenum. So this extra electron, now if it is in the 3H phase, you can remember this crystal field diagram again. So this extra electron will go to the higher energy orbital here, whereas in the octahedral case, now there is one lower energy orbital which is still vacant, so it will go to that particular orbital. So because of this, you can see that the final product here has a higher energy when compared to this octahedral configuration. So from this, we try to say that as we increase the concentration of the rhenium, because of this extra electron will always try to go to a lower energy state, there is going to be a transformation to the octahedral configuration or the 1T prime phase. And yeah, and so these are some of the optical images and the AFM images of the alloys of these kind of alloyed or rhenium doped MoSe2 systems, which we had grown on sapphire substrate. And these are the Raman spectrum of that. So you can see that as you increase the amount of rhenium, you can see that there is a clear change in the Raman spectrum, and you can see it going from the MoSe2 kind of spectrum to that of the ReSe2 kind of spectrum, where there is additional peaks are becoming visible. And also we can substantiate these results by also using the XPS. So in XPS also, because the crystal field is different, or the binding energies are also going to be different when you are having a 2H phase coordination, or when you are having the 1T or 1T prime phase coordination. So because of that, you can see that as you keep on increasing the concentration of the rhenium, you can see that the MO, the binding energies are shifting from that of a 2H coordination to that of the octahedral coordination for the 1T prime. So from the Raman and from the XPS, we can confirm these results. So another important characterization technique to study this phase transition is the STEM, scanning transmission electron microscopy. So these were samples, and these were done at Oak Ridge National Lab. And you can see that if you dope a smaller percentage of rhenium into MoSe2, you can see that it still prefers to be in the 2H phase. Whereas if you increase the concentration of rhenium, there are two possibilities that can happen. Either there is agglomeration of these rhenium atoms, or you can see that there are regions where there is complete transformation to the 1T prime phase. Okay. So this is basically the STEM image for the 1T prime phase of pure ReSe2, and you can compare that with the rhenium doped MoSe2, where rhenium concentration is close to 80%. And you can see that there is a clear structural transition that has taken place. Now, another interesting aspect of having rhenium doping was, so because of, if you see the earlier diagram, so here you can see that the rhenium is having one additional electron, and this is basically now unpaired. So the question what we asked was, can this give rise to any interesting kind of magnetic behavior? And the answer, and we had done some theoretical calculations. These are quantum molecular dynamics calculations. which predicted that in both the cases where we have 2H structure and 1p prime structure with rhenium doping, it was predicted that there is a small amount of magnetization per chemical unit. And our squid measurements on these samples also showed that there is a small, it is weakly ferromagnetic, and this ferromagnetic behavior, it persists till room temperature. Okay, so this can be, this system can be interesting because, this kind of dopants can give rise to magnetic properties in 2D materials even at room temperature. So this is one of the way in which we can engineer the phase transitions, that is by alloying. There are, other ways also by which you can do this. So with this in mind, we started looking at, some of the different aspects. That is, first of all, if you want to use these TMDs in applications like, ultra-fast photodetectors or valleytronics or field effect transistors, now, theoretically, it has been predicted that these materials have high quantum efficiency photodetection because they have very large optical absorption coefficients and long photoexcited carrier lifetimes. But actually, if you measure their lifetimes experimentally, you can see that for the monolayer TMDs, it is of the order of picoseconds. So this show, and also they showed very low photoluminescence quantum yield even in the monolayer limit. So what can be the reason? Obviously, there are a large amount of non-radiative recombination processes which is giving rise to this low PL quantum yield. And if you see these kind of systems, they are notorious for having these chalcogenide vacancies like sulfur or selenium vacancies. And these kind of vacancies can give rise to mid-gap states. And these mid-gap states have been investigated using pump and probe techniques. And people have seen that these can give rise to trap-assisted recombination. So this basically reduces the radiative recombination process, and the trap assisted recombination or the Auger recombination processes dominate, and you get these kind of non-radiative recombination processes. So so one of the things is, so if you're having these kind of so what we see is that this is actually in the presence of the defects. But even when there are no defects, okay, in the case of say Scotch tape exfoliated monolayers at high charge carrier densities, still it was seen that non-radiative channel is the dominant energy loss pathway. So what is the what are the possible reasons for this? So one of the possible reason is, so you have initially the photoexcitation of electron hole pairs, and this non-radiative recombination of these electron hole pairs happens, and that basically transfers the energy to the lattice. And so there is a local heating of the lattice, and then this heating of the lattice occurs in the time scale of around 10 picoseconds, and after that there is a cooling of the lattice which is observed at in the time scale of around 100 picoseconds. So what we tried to do, what we were interested was whether we can utilize these kind of phononic excitations or these kind of local temperature increase in the lattice for triggering any kind of light driven atomic motion, which can give rise to structural phase transition. So this is another pathway by which we wanted to we wanted to study structural phase transition. And so these were not very well understood because we didn't have experimental techniques which can actually quantify the atomic motion and lattice temperature directly. So this is where we started collaborating with the Stanford Linear Accelerator facility. So they have a technique which is called as ultra-fast electron diffraction. So in this technique, what you do is, so you basically excite your system, your sample, which this is basically in the transmission mode. So you excite your sample with a femtosecond optical pulse, and then you study, you send a electron beam or electron pulse of very high energy, and you study the changes in the diffraction pattern. Okay, so this is the technique which is called as ultrafast electron diffraction. And using this technique, you can actually study the electron phonon coupling, and you can understand how this local changes in the temperature takes place, and how you can relate the atomic motions to that. So this was our sample. So we drew the MOSE2 system using CVD, and these are then transferred into 10 nanometer thick silicon nitride films, and then the experiment is carried out, and you can see that how the intensity of the different spots in your electron diffraction pattern changes as a function of the delay time. So what you can see is, so as the temperature increases, basically the thermal motion of the atoms increases, and this basically reduces the intensity of the diffraction spots. So this is what is called as the Debye-Waller factor, and from this Debye-Waller factor, you can see that the change in this intensity is equal to the exponential of delta U square, that is the mean square distance of these vibrations, atomic vibrations, into the Q square. And so what we have done is, so for MOSE2, we have used two excitation energies. So one is at 400 nanometer excitation and one is 800 nanometer excitation. So the reason is 400 nanometer excitation gives rise to a large number of hot electrons, whereas the 800 nanometer excitation gives rise to banded carriers. Now, here you can see that, so for the different diffraction spots, or the corresponding to the different planes, you can see how the intensity is varying. This is the different energy, the incident optical pulse energies, which will give rise to the different carrier densities, which are indicated here. And this is the change in the intensity as a function of the Q square, which is corresponding to the different, basically the different diffraction planes. And now you can actually plot this normalized intensity with respect to the delay time of the pulse, of the electron pulse that you are giving. And what we see is that, so as you go to increased carrier densities or higher optical fluences, we see that there is a significant shift or significant deviation for the complex Bragg peak intensity. And this actually suggests that there is some kind of an energy redistribution between different phonons, which is happening at very high carrier densities. So these results were then studied by using non-adiabatic quantum molecular dynamic simulations. And what we see is, you can see how from these, you can actually calculate how the lattice temperature is increasing. And also first principle DFT was done. And this is basically at zero carrier density, and this is at the highest carrier density which is corresponding to the highest fluence which we have excited the sample with. And we can clearly see that there is a softening of certain modes here. Certain phonon modes are getting softened. And if you see the eigenvectors for these soft phonon modes, you can see that at the M point, there is a kind of dimerization that is happening. So this kind of dimerization can actually lead to structural phase transition. So this is one of the pathways by which we can try to engineer the structural phase transition. So the idea here was, so the idea here was, so we wanted to study photo-induced structural phase transition, so that later on you can basically use laser-induced phase patterning for these 2D materials. So this was done initially for the MOSE2 system. And later on, we have also done these experiments for a molybdenum telluride system. So in the telluride system, the difference in the energy between the two different phases, that is the 1T phase, 1T prime phase and the 2H phase, is relatively smaller. And the UET experiments actually indicated some very interesting results in the case of MOTE2. So you can see that unlike the earlier case where all these spots were weakening, so the blue color here indicates that the intensity is reducing, and the red color here indicates that the intensity is increasing. So some of the spots, the intensity is increasing, whereas some other spots here, you can see for the other diffraction planes, you can see that the intensity is decreasing. So this was kind of interesting, and it was studied by using, it was studied, and what we have seen is that, so there are two different relaxation mechanisms for these carriers. So if you're exciting with higher energy photons, then you have a large amount of the hot carriers, and these hot carriers which are excited by the high energy photons, they relax by coupling strongly to the zone center vibration modes. So this is the intra-valley relaxation where the coupling is strongly to the zone center vibration modes, and the resultant, and basically here there is a complete conversion of the optical energy into the atomic motion here. Whereas if you are exciting with 800 nanometers, and if you are looking into the band edge carriers, then you can see that there are different kind of intervalley relaxation mechanisms that are possible through different phonon modes. So basically from these experiments, we had concluded that, using the using light, or we can actually try to exploit how the phonon dynamics can be used to study any kind of structural phase transitions. So now I will come to some of the work that I am doing currently. So let me start with the concept of twisted bilayer transition metal dichalcogenides. So this is a very interesting system. And as you can see, so once you twist one layer of TMD over another layer of TMD, you can see that there is a significant change in the band structure. So here, basically, this is the band, this is the parabolic band of one layer, and this is the parabolic band of the other layer. This is at the K point, and this is at the K prime point. But what happens is, because of the coupling or the increased hopping of the electrons between these two layers, you can see that now there is going to be a hybridization gap. And this basically this band here is it can be extremely flat, and at certain angles it becomes very flat, and at that angles which are called as the magic angles, there are predictions of interesting phases like the correlated insulator phases at half filling, and zero resistance pockets which correspond to superconductivity. And also there are interesting predictions of metal to insulator transitions. So I will not go into the details of it, but this is something which is very interesting, because you can get a whole lot of new phases emerging just by twisting one layer of one layer of material over the other. Now, so in our lab, we basically make the TMDs by two techniques. One is through the mechanical exfoliation, that is, we peel the bulk crystal by using a scotch tape, and the other one is using chemical vapor deposition. So, so some of the samples like graphene, HBN, we do mechanical exfoliation, and the TMDs, we try to grow them by using the chemical vapor deposition. Now, so this is the setup where we have grown initially the WSE2 samples. And one of the interesting things that we have observed is that basically the role of hydrogen in determining the growth of WSE2. So what you see here is basically how your tungsten trioxide, which is the precursor, the tungsten precursor for the growth of WSE2, how as a function of temperature, what are the different oxide conversions it can go through. Okay, so we are flowing some hydrogen in the system. Even if we don't flow hydrogen, With increase in temperature, you can see that WO3 goes to WO2. Now, what we have done is we have studied what happens to our precursor under different hydrogen flow conditions. So when there is no hydrogen flow condition, the precursor remains as such after the growth. Whereas if you are having if you are having a continuous hydrogen flow, that is, starting from 200 degrees Celsius to the growth temperature of 800 degrees Celsius, continuously, if you are flowing hydrogen, then you see that there is a conversion of WO3 to WO2. Now, this is not good for our growth because WO2 has a higher, sublimation temperature. And because of that, we do not see the growth of WSE2. So what we want to do is we want to basically catch some of these intermediate species which are highly reactive. And these are the species, especially this W18O49 is a species that reacts with selenium and converts to WSE2. Now, to get this guy here, what we have done is we have actually flown hydrogen only very near to the growth time. That is, you start flowing argon from room temperature, but only when the temperature is around the growth temperature of 800 degrees Celsius, like once it reaches 700 or 750 degrees Celsius, you start flowing hydrogen. So what hydrogen will do, it will slowly convert this WO3 to this reactive species. And this reactive species, now it immediately reacts with the selenium at this temperature and then gets converted to WSE2. It does not, it actually prevents the formation of WO2 in the system. So in this way, we have been able to grow very large WSE2 flakes of the size of around 60 microns. And some of the interesting samples, what we observed were these bilayer samples of WSE2. So this is basically the 3R stacked WSE2, and this is the 2H stacked WSE2. Okay, so so this is something which I have explained before. But the thing is, optically, you can see and you can understand that this is 3R and this is 2H, and this has been reported in several literature as well. Now, we wanted to study what are the spectroscopic signatures of these. So what we have done is we have done Raman spectroscopy. And this is just to tell you how the Raman spectrum looks like for WSE2 monolayer and 3R and 2H bilayer. So you can see that in the monolayer, apart from the fact that the separation between so basically one of the issues with WSE2 is you have an almost degenerate A1G and E2G peak. So E2G corresponds to the in-plane vibration and A1G is the out-of-plane vibration. In most of the other TMDCs, these two peaks are separated. So because of that, by seeing what is the difference between the Raman shifts of these peaks, you can actually see whether it is a monolayer, bilayer, trilayer, etc. But in this case, since these two are almost degenerate, it becomes very difficult to say whether it is a monolayer or bilayer. So one of the interesting features in the bilayer samples, what we see is the extra peak here, which is called as the B2G peak. And this B2G peak is actually absent in the monolayer WSE2. So from the so by looking at whether you have the B2G peak or not, you can clearly say whether it is a monolayer or a bilayer or multilayer WSE2. Now, so this is basically the optical image which is having both the 3R stacked and the 2H stacked WSE2. Yes.
Yeah. So I have one question. This B2G peak, does it come from the interlayer coupling?
Yes, it is coming from the interlayer coupling.
Okay.
Okay, but this is actually absent in the case of the monolayer. Okay. So from this, we can clearly say whether it is a monolayer or a bilayer. Okay, so that is one of the ways in which from Raman we identify for WSE2 especially whether it is a monolayer.
Okay. And is this mode polarization active?
Which one? The A1G?
B2G. The B2G. In bilayer or 2H bilayer or 3R bilayer.
Yeah, actually, I'm not very sure because I have never done this polarized Raman. We
Okay.
don't have the facility, so I'm not very sure about the polarization dependence of this.
Okay. Okay. Thank you.
So here, if you see, now you can see that this is basically the Raman map of the same region. And interestingly, what we see is that in the Raman map, you can see that for the 3R region, the intensity is lesser than the single layer region. And for the 2H region, the intensity is much larger than the single layer region. Whereas if you see the case of PL map, you can see that in both the cases, you can see that there is a quenching of the PL because of the fact that you're going from a direct band gap to an indirect band gap. Okay, so 2H and 3R both are having indirect band gap. And because of that, the photoluminescence intensity is highly reduced when compared to the photoluminescence of the monolayer. So this one was very interesting for us, and we can see that there is a very sharp the contrast in the intensity of the 2H and the 3R. So we decided to try to understand why this is happening. So the explanation for this is, so you can actually attribute it to the Resonant-Raman features. So as you know, what is Resonant-Raman spectroscopy? So in Resonant-Raman spectroscopy, so suppose if the excitation energy is matching with any of these electronic excitations, then you will see that there is a large transfer of energy to the phonons, and basically you see that in the Raman shift. Okay, now in your structure, so this is your band structure for the bilayer, and you can see that you have the direct excitations here from the valence band edges, spin orbit split valence band edges that gives rise to the A and B excitons. And at the same time, there are features in the band structure which are resulting in nesting. So what does actually nesting mean? So in the band structure, there are regions where this conduction band and the conduction band and the valence band are parallel to each other. So in this case, what happens is, so suppose if you are exciting electron from the valence band to the conduction band with a photon, now this produced electrons and holes will propagate with exactly the same but opposite velocities because your curvatures are the same here. And also this gives rise to strong van der singularities in the density of states. Okay, so because of this, so if the C exciton features are matched in your Resonant-Raman spectroscopy, then because of this huge density of states, you can see that there are a large number of unoccupied states to which you can excite the electrons, and that can give rise to strong features in your Raman. So now, if you see the band structure of 2H and 3R WSE2, and you can actually from this paper actually calculated the absorbance percentage and the oscillator strength as a function of energy. Now you can see that the at 300 Kelvin, the C exciton peak positions it occurs at 542 nanometers in the 2H WSE2 and at 553 nanometers in the 3R WSE2. And we have used an excitation wavelength which is 532 nanometers, which is very close to the exciton peak positions to the basically the energy differences for the C exciton peak positions in 2H WSE2. So this large Raman intensity can be attributed to this resonant features in this C exciton peak position. Now, one of the interesting aspects of trying to do this is, so during our growth, other than these triangles, we also see very interesting, patterns like these. And these are actually called as kirigami structures. And these kirigami structures actually arise when you have non-equilibrium growth conditions. And if there is a lack of local supersaturation on certain areas of the substrate, then what happens is instead of sample going and adding to the already grown layer, it actually starts happening the reverse way. So what happens is the sample will, the molecules will start to move away from the sample, and there will be an etching of the top layer of the WSE2. And this happens in along certain crystal directions symmetrically. And that is why you see that, there are these kind of patterns which are called as the Kirigami patterns. So these patterns, now, if you just take an optical look of it, you cannot say whether it is a 2H type or 3R type stacking. So once we do this resonant Raman spectroscopy, now you can clearly identify, and you can say that K1 and K2 are basically having 2H stacking orientation, whereas K3 and K4, these are actually having 3R. So because of the contrast difference, you can clearly say what is the stacking orientation in the bilayer WSE2. So this is this is a technique which we have developed specifically for WSE2, and we can actually use the same technique for other kind of to study other kind of TMDs if you are having a variable wavelength light source. And not only that, so these are some of the interesting growth features. If you want to study in detail, you can actually do this Raman map. Like, for example, you can see there is a bilayer WSE2 here. But if you see the Raman map, you can see that this region is 2H stacked and this region is 3R stacked. Similarly, there are other regions here. Optically, it is not distinguishable. But if you see the Raman map, you can clearly see that there are regions where 3R stacking is favored, and there are regions where 2H stacking is favored. Okay, so this is interesting from the growth perspective, and also to identify if you are having a continuous bilayer growth, whether it is 2H or 3R stacking type. So we can use this Resman-Raman spectroscopy technique. Now, apart from so now let me talk to you about how we make twisted bilayer TMD. So I have already told you how we grow these TMDs, and our idea is to basically make twisted bilayer TMDs with different twist angles. So this is the setup what we have in our lab, and it consists of stamp stage and a sample stage which is having this rotation degree of freedom. So you can place one sample, one layer of WSE2 on the sample stage, and the other one on the stamp stage, and try to rotate it. And the idea here is basically now it is much more easier to do this for the case of CVD samples, because we have well-defined shapes, and because of that we can easily try to identify what is the angle of this twist. But the problem here is that when we try to pick the sample from the as-grown substrate, which is the silicon dioxide, we have some issues. So let me explain to you how what is the technique, and how we have overcome this problem. So what we do is the substrate on which we have grown the silicon dioxide, it is placed on the substrate holder at 65 degrees Celsius. And then from the stamp stage, you place a cover slip with a PDMS and PPC coating in this kind of a hemispherical shape. And this is brought in close proximity. And first we take one HBN. And once we attach this HBN, now this HBN is again placed on top of this WSE2 wafer. And the problem is on the as-grown wafer, the coupling of WSE2 to the substrate is very large, that it becomes difficult for the HBN to basically remove this WSE2 from the as-grown wafer. So what we do is we inject some water at this interface that loosens this WSE2 because of the hydrophilic nature, and WSE2 actually gets stuck onto the HBN, and we pick up this monolayer WSE2. Then again we can place this on another layer of WSE2, and we can give the desired twist, and then try to pick it up, and then you can place it on a fresh wafer. So in this way we have made several we have made several twisted bilayer TMDs of different angles. And we have carried out Raman studies on these twisted bilayer WSE2. So what we see is, so this is the Raman spectrum for the monolayer, and this is the position of the A1G peak. And if you see, as you go on in changing the angle, you can see that there is a shift in the position of the A1G peak. But if you, so this is a 3R and this is the 2H. You can see these are the 3R and 2H. And if you plot this Raman shift, you see that close to the angle of 30 degrees. Now this peak is exactly coinciding with the peak of the monolayer. And also to add on to that, what we also see is that the B2G peak, which is present in the 2H and the 3R stacked WSE2. So this B2G peak actually gradually goes away. And as you reach 30 degrees Celsius, there is absolutely no evidence of a B2G peak. So this is interesting because this clearly says that there is a strong decoupling between the two layers as you increase the twist angle from 0 to 30 degree, okay, or from 60 degree to 30 degree. So let us try to understand. Further, we have also done the PL spectroscopy of these twisted bilayer WSE2. And what we see is, so at angles away from 30 degree, like 70, 20, 43, 46, which are closer to your 2H or 3R stacking, you can see that in basically the overlapping regions, there is quenching of the PL. So that means that here you have here you are having a indirect band gap, just like that of the 2H and the 3R bilayer WSE2. Whereas if you go to 30 degree, you can see that in the overlapping region, there is no quenching of the PL. And this has been seen in more samples of 30 degree twisted WSE2. And this clearly shows that now these two layers are actually behaving as two independent, monolayers. So because of that, your PL intensity is not getting quenched, it is just getting added up. Okay, so you are basically seeing the PL intensity from two separate monolayers here, whereas in the other cases, because of the coupling or the hybridization of the PZ orbitals of your selenium, you see that there is a transition to an indirect band gap, and that basically reduces the PL intensity. So, this is your 3R stacking. And so we will try to understand why this decoupling is happening. And this is your 30 degree, and this is basically your 2H. So you have to rotate by 60 degree. Now, if you see, compare the three different, stackings here. Now, what you can see is, so in certain cases, what happens is, so each of these atoms, it occupies a certain amount of space. And inside that space, if there is another atom which is coming directly on top of that, that will lead to strong Coulomb repulsions, because there is going to be a overlapping electron cloud, which will significantly increase the potential energy, and that will give rise to repulsions, and this is called as steric repulsion. Okay, so this is what happens when you go to 30 degrees. So near to 30 degree, you can see that there are places where you can see there is very strong steric repulsion, whereas if you see the other cases, like close to the 2H or the 3R, now these repulsions are reduced, and these are in the energetically favorable stacking configuration. So using this, what we can see is, so whenever you are having this kind of a twisting, there is, the interlayer coupling is significantly disturbed because of the steric repulsion. And along with the interlayer coupling, the hybridization of the orbitals in the two layers, this is also going away. You can see that there is, as the distance between the atoms are increasing, the hybridization is also going to reduce. So because of this, now you see that there is a crossover from indirect to a direct band gap structure. So this is what we have done in the case of WAC2, but we have also done the same thing in the case of bilayer graphene as well. We wanted to study how the interlayer coupling changes in the case of bilayer graphene and what are the Raman signatures. So this is just to show you the how the Raman spectrum originates for the monolayer graphene. So this is just the 2D peak, how the 2D peak. So G peak in graphene is basically from the intra-valley scattering. And for the 2D peak, you have the inter-valley scattering, which is facilitated by the phonons. And in the case of bilayer graphene, now because you are having these two layers, now you are having a total of 4 different possibilities, and your 2D peak in bilayer graphene is comprised. You can actually basically it comprises of 4 different peaks, which you can do a peak fit, 4 peak fit. So, so we know how the Raman spectrum looks like for the case of single layer graphene and bilayer graphene. But what about twisted bilayer graphene? So now in the case of twisted bilayer graphene, what happens is now these are the 2 different layers, and the brilliant zones are now shifted or rotated by an angle theta. And depending upon that, now you can see that these are the Dirac cones at each of these K points, which are here. But there are places where these two curves can actually touch each other. And at that point, there is a hybridization. And that basically gives rise to this. Basically, it opens up into these kind of subbands. And you can see that this subband actually gives rise to a Vanno singularity in the density of states. And here what we are concerned with is in this kind of a structure, how the Raman scattering takes place. So this is the picture for the G-band excitation. So suppose if the energy of the laser, so this is a condition which is given, which relates the angle of this a twist with the energy of the laser. So at this particular twist angle, now the separation of the van of singularities here is equal to the energy of the laser. Okay, so suppose if you are exciting with a 532 nanometer laser, that is around 2.3 eV. So you see that now the separation between these van of singularities is 2.3 eV. Then there will be a huge increase in this G band resonance. Okay, so this is giving rise to a resonant Raman feature. And you will see that there are a large number of excitations happening here, and you get relaxation through phonons. And whereas the 2D band is actually a little bit more intriguing. So there are 2 possibilities. So if your energy is lesser, then you can have these kind of transitions, which are basically equivalent to the transitions like that of a single layer graphene. Or you can have transitions which are going to these van of singularities through this van of singularities. So these can basically at these critical angles, you can have this kind of scattering, which is inter-valley scattering, which is assisted by the phonons, which can happen. So what we have seen in our Raman spectrum is, so for our value of the laser, which is 2.3 eV, we have calculated the critical angle, and it is around 12.5. So we have actually fabricated a twisted bilayer graphene at angle of 12.5, and we indeed see that there is a huge increase in the resonance of the G band. And also for the 2D band, we see that there is, so this is some result that we are still trying to analyze, but we see that the 2D band is also slightly different from that of the other angles, because we see that there is an additional component or an additional peak that can be fitted for the 12.5 degree angle. Okay, so this is interesting. And this also shows that, how the mechanical degree of freedom, that is your twist angle, is closely related to your electronic degree of freedom, which is basically arising from the, van of singularities in your in your energy spectrum. Okay. So now the last part of the talk, I will just give you a brief glimpse of what are the materials that we are currently growing in our lab. So as I've already told you, we had started growing WSE2, and initially we were growing it on silicon oxide. And later on, now we have also tried to grow this WSE2 on top of other 2D materials. Like for example, what we have done is we have exfoliated HBN and graphene or graphite on silicon oxide, and these were placed inside the chamber, CVD chamber, and we see that you can grow monolayer of WSE2 nicely on top of this HBN and graphite. So this is interesting because I mean, this will give you a very nice coupling between the two 2D materials. And if you can make graphene and HBN on a larger scale using CVD, then they can be directly used for a large area growth of WSE2 or any other TMDs. And the other thing that some of the other materials that we are looking into is one is the NBSE2, the niobium selenide. And so these are some of the optical images and the Raman spectrum. So this is for very thin layers. This is how the Raman spectrum looks like. And it evolves. This is how it evolves into when you go to the when you increase the thickness of the NBSE2. So this is done by using salt assisted CVD growth, because the precursor that we are using, that is NB2O5, it has a very high melting point. So in order to reduce a melting point, we actually mix that with NaCl and then we grow, and we are able to see some growth of NBSE2. And another thing what we are trying to do is growing niobium doped WSE2. And so we have basically put in the precursors of both tungsten and niobium, that is W3 and Nb2O5 inside our furnace. And we see that, and basically here we are growing it on a sapphire substrate. And what we see is at different points, we can see that there are differences in the Raman spectrum. So this basically looks like a Raman spectrum for the 2H type WSE2. But if you see here, this basically has much lesser intensity. And also you can see that, there is some additional peak which is coming around 120. And actually, these are the features of 1T phase of, WSE2. So we are currently trying to investigate whether with niobium doping, they are able to induce a change in the structure from 2H to 1T phase. So this is again still, we are trying to study this. And we have also grown some 2D oxides like WO2. So this is a metallic oxide. And you can see, these are the Raman features of WO2. It is in monoclinic form. And these are the XPS spectrum to confirm that it is WO2 and not any other oxide of tungsten. And this is the latest result. Actually, in fact, from this week, what we have seen, we are also trying to grow some 2D van der Waals magnets. And we have started with chromium telluride. So chromium telluride is interesting because it has so many different, oxidation states. You can have CrT2, CR5TE8, CR2TE3. There are so many different oxidation states for this chromium telluride. And we are actually seeing probably, I think it is CR5TE8, but in the same wafer, we can actually see both trigonal structures as well as monoclinic structures. So it will be interesting to investigate how, the magnetic properties are going to be different for the different type of, crystal structures in these van der Waals magnets. So with this, I would like to conclude my talk, and I would like to acknowledge all my collaborators. And this is my current group at IIT KGP, and I would like to acknowledge all the funding agencies. And thanks for your kind attention.
Thank you, madam, for a very nice talk. Now the platform is open for questions from audience. So if you have any questions, please ask.
Hello.
Yes.
So and the slide where you have shown the evolution of Raman with the angle, stacking angle.
Hmm.
So this experiment was performed with what grating, like in which resolution?
This one, right?
The left one.
This one, right? I
Yeah,
mean, it's the same spectrum.
yeah.
So this was done with 2400.
Okay. So the shift that you are saying here is within, I guess, 1 centimeter inverse, right?
Yes.
So is it will it not be within the means it can will it be resoluted in this setup in
Yes,
2400?
you can actually clearly see the shift between the monolayer and the bilayer. And we have actually done this monolayer and bilayer, and we have actually compared that with the literature values. Following that, we have done for the other samples.
Okay. Okay.
And actually, that is why I was saying. So basically, the case of WSE2 is a little bit tricky because in WSE2, both A1G and E2G are almost degenerate, whereas in the other TMDs, so these are like two separate peaks. So you can clearly see the shift in each of these peaks, whether the peak shift is reducing or increasing, and we can reach some direct conclusion. But here it is a little bit more tricky, but so that is why we have also shown this B2G peak here, that the B2G peak is clearly going away as you increase the angle to 30 degrees. Plus, additionally, the photoluminescence also shows that there is a clear decoupling between the two layers.
Okay.
Okay, so we are doing a complete spectroscopy study, both Raman, and we are correlating that with the PL as well.
So in this 30-degree PL map, so in this case the layers are decoupled, right?
Yes.
So in this middle area, I can see a small blackish area where it should be like double of each of the monolayers intensity, but it looks like the intensity is slightly is less compared to the monolayer, uh, if I am not wrong.
I think this has to be. Actually, we have data for several other samples as well, but actually, the if you compare the actual intensities, it is kind of difficult because here the PL intensity is also dependent upon what is the defect concentration. So, if
Hmm.
the defect concentration on the two layers are different, there could be some kind of, quenching which is happening.
Okay. So that might so the case would be not a simple addition of two PL in
It
that case.
might not be.
Okay. Okay. Thank you.
Um, are there any more questions?
So I have one more question. So you said that the resonance is the resonance Raman resonance wavelength you were choosing by matching the energy of C exciton and the excitation wavelength. So
Actually, what happened is in our case, in our Raman, we have only one laser, that is the 532 nanometer,
uh-huh,
and it happened to match with the WSE2C exciton.
okay.
But if you want to do this as a more rigorous characterization technique, then you need to have a variable energy laser source,
Hmm.
and then you can actually change the energy as a energy, and you can measure the Raman, and you
Hmm.
can see where the resonance conditions are happening. So
Okay.
if you do the same experiment with, like, say 633 or 410, then
Hmm.
your results will be drastically different. So
Okay.
just because we are doing it at 532, we are able to see this resonance.
So this resonance could be with other A or B excitons as well. In that case, also the same resonance will happen, right?
Yes.
Okay. And in this sample, did you in the PL spectrum, did you see the C exciton in your spectra?
No. Actually, we don't have the range to go till C exciton.
Okay, okay. So it's basically you're saying that resonance is all means the resonance is happening because in literature is already established that C exciton should be at that energy range.
Yes. So the C exciton features, there are band structure calculations from which you can actually see where the C exciton should be. And if you actually see this energy varies as you change the temperature. Okay, so as you change the temperature, then these energies might vary and you might lose the resonant condition also. So at room temperature for this system, this is a resonant condition which is giving rise to this kind of a contrast difference. But maybe, this is basically how you can characterize a sample with very standard techniques of Raman and PL. Okay, so any sample that we make with CVD, this is the basic techniques, Raman and PL. And with Raman and PL, you can clearly see how the interlayer coupling is changing. So that is why, so we have done one experiment with the WSE2, and then the next experiment we had done with graphene. So because people can ask, like, for example, if you are doing this, artificial stacking, is this stacking as good as, growth, CVD growth of bilayer graphene with 12.5 degree twist? So the answer is yes, it is as good as it, because we are able to see this resonant condition. And this resonant condition says that there is a strong coupling between the two layers, and we are having these Vanov singularities, which are again matching with our laser's energy. So we have actually calculated this angle using this formula. Then we made the sample, and then we can see this resonance clearly.
Okay. So I was just curious because in CVD grown samples, because of varying strain, these peaks might shift a little bit, this excitonic peaks. So that can move your sample from resonant condition. That's why
It is possible. But I think within 20 nanometer, 20 to 20 nanometers around, I think it should be okay.
Okay. Thank you.
Yeah.
Yeah, I have some questions. You talked about alloying of these 2D materials. You are
Yes.
mixing this WO3 and MO3 and sulfur and selenium together. So
Yes.
do you get any in-plane heterostructure by that, or is just the alloying only?
Okay, so that's a good question. I have not presented those results. So what we see is it depends upon the temperature. So if you are at very low temperature, like around 600 to 650 degrees Celsius, there is a high chance of formation of in-plane heterostructures. And in between region, there is a, alloying temperature regime. And at very high temperatures, there is a formation of vertical heterostructures.
Okay, so in lower temperatures, favorable to in-plane heterostructures are favorable.
Yes.
Okay. So another thing is that you picked up this WSE2 with HBM. So it's DI water necessary to pick them up. And what is the success rate you have seen?
So actually, the reason why we have used DI water is we are trying to pick up the WSE2 from the as-grown wafer. The as-grown wafer means it is the wafer on which you have grown WSE2, and it has seen very high temperatures of like 800 degrees Celsius. And because of that, it is the WSE2 which is grown is very strongly coupled to the surface. It becomes impossible to remove it. Only way is you have to etch off the silicon oxide and then transfer it. So we didn't want to do that kind of a transfer. So that is why we tried to pick it up directly using HBN, but we were not able to. So we decided to loosen this WSE2 a little bit by injecting water. Because people have tried transfer techniques, large area transfer techniques of TMDs using water delamination. So what we have done is we have combined this standard pickup and transfer technique for the making 2D heterostructures with this water delamination, so that it will loosen up the WSE2 and it gets easily picked up on the HPN.
Okay. And the thickness of HPN does it play a role to pick?
Actually, it does, because for the case of graphene, we have been able to pick graphene even with some monolayer HBN. But for other samples, actually, you have to calculate the surface energies for HBN and for the other 2D material that you're trying to pick using HBN. So it will depend upon how the adhesion energies are different for these two systems. If there is a very good adhesion energy, then you can easily pick it up using HBN. So HBN is preferred because it is having adhesion energies which are very close with the graphene and TMDs. But for certain other 2D materials, like for example, we have been trying to pick up chromium fluoride using HBN. We have been finding it slightly difficult. So yeah, so even with thicker HBN, we were not being able to pick up certain 2D materials.
Okay.
But actually, you have to optimize the transfer technique, because maybe if you use a different polymer, like say PC, which can go to higher temperature, then you might be able to pick up at higher temperature. So it is always an interplay. You need to study the adhesion energies as a function of temperature and see what would be the ideal temperature range for picking up each sample.
Okay. And you have also grown this NBAC2. Are they stable in ambient conditions?
We have seen that beyond a week, it is not that stable, but within the week, stored inside desiccator, it looks fine.
Okay. Thank you very much. Is there any other questions from the audience?
I have one more question. So in the transfer system, that slide. So in the last, or maybe in the other step, you are picking one of the TMDs with another TMD. So how much is the success rate of that step? Like after twisting, you are picking the
Actually,
whole stack.
if we inject DI water, then it is 100%.
Okay, so without DI water, it's difficult.
No, it is difficult.
Okay, okay.
So, I mean, injecting DI water kind of loosens the interaction with the substrate, so it gets easily picked up with the other 2D material.
And
One more thing to tell you here is it also depends upon the interlayer coupling. For example, as I showed you here, for the 30-degree sample where there is the interlayer coupling is very weak, we have found it is much more difficult to make those heterostructures.
okay.
It
So
doesn't get picked up easily.
so this is done after you are twisting the sample, then you are picking the
Yes.
whole stack. So
Yes.
is there any chance of relaxing during that step? This angle can relax back to its aligned position.
So actually, what we have done is we have compared this results of the Raman, and we have also annealed this sample at temperature of 200 degrees Celsius in vacuum, and then again did the Raman. So we don't find any stark difference. So we are not seeing any kind of relaxation later on.
Okay, okay. Thanks.
Are there any more questions? If there are no questions, we would like to thank Dr. Vidya Kochat for this nice talk. We will like to have you somewhere then either Pune sometime in person. Yeah.
Okay.
Thank you very much.
Thank you for the attention.
Thank you very much.